Yeah. Hello, everyone. Welcome to the Graphics Programming Virtual Meetup. Today, we will continue talking about PBRT and starting from chapter 3.9, where we talk about transformation. So a transformation map, either a point or a vector. The transformation itself can be arbitrary, but in here we talk about what kind of a subset that can mainly it can be represented by matrices. So it need to be linear. And also we want to have its inverse, so it needs to be one-to-one and invertible. And continuous is just also a nice property to have. And 4x4 matrix can be shown to express the linear transformation of a point of vector. So here are two different ways that a matrix can be interpreted. One is transformation within a frame. So given a point, the matrix can represent a new point in the same frame, or transformation from one frame to another. So that's something that cannot be captured by the type system, for example. Just something keep in mind when we use those matrices. And most use of transformation in PBRT are transformation of points from one frame to another. Here is a very quick introduction or just refreshing to the homogeneous coordinates, which is also used in PBRT. So giving a frame represented by a point and three basis vectors, there's an ambiguity between a point and a vector. So we can represent a point as inner product of the x, y, z, and 1, this vector to the frame, and the vector as inner product of x, y, z, and 0 to the frame. So this additional coordinates is called the homogeneous coordinate. And the fourth coordinate is sometimes called weight. And to convert homogeneous coordinate back involve divide by W. So in this perspective, vector really can be seen as infinitely far away points, because when the W is 0, when we divide by W is infinitely large. So PBRT does not have a homogeneous points class, something like this, but a lot of transformation routines will use homogeneous form because it's easier to deal with. And PBRT defines a transform class, which just represent a 4x4 matrix. It has a lot of method to help. And its member is the 4x4 matrix and its inverse. Because it is kind of computational expensive to compute the inverse on the fly, so PBRT decided to cache it. I think a lot of ray tracers do the same to cache the inverse. So since this representation of transformation is relatively memory hungry, PBRT decides to have another interaction, and then they can use something like an internal cache to share memory. So transformation by default is an identity matrix. It can be created by a matrix. In this case, we compute its inverse, and if it's not invertible, then we know it's a bad matrix. Then we just fill every number with nan. And translation in homogeneous coordinates is just the last column. And the math works for both point and vectors. For point, it does the translation. For vector, it does nothing, basically. And scaling is a diagonal matrix. And x, y, z axis rotation. This is just generalized 2D rotation into 3D, so we can see this kind of sine and cosine term. We just put them in.
Trying to understand why the cosine and negative sign appears there is a bit complicated, but it's a fun exercise.
Yeah, this is, I think, a useful way to think about that is just think in 2D, right? This basically 2D rotation, so just think it in 2D and this is the basically 2D rotation matrix, and then the problem is why it's negative. It's just envision trig in your head, basically. Envision how the basis vectors are rotated.
Yeah, the 2D rotation matrix is a really nice one for explaining matrix stuff to people sometimes.
Yeah.
Because you can figure out how the sine and cosine relate to how it
Oh, they even have a nice diagram here. Now, this is complicated. This bit of math is basically I learned a few years ago, and afterwards I forgot. And then afterwards, I just copy and paste.
Yeah, yeah. There's some good short versions of this that get passed around for shader stuff. Yeah. There's one.
I think I learned this from that that Professor Ravi something. He's very famous for like pre-compute radiance transfer kind of stuff, and yeah, he also had a graphics course, and I learned it from him. You probably can't understand this by reading this section, though.
Uh,
I will try to find a link afterward. Find a link for the video on this. So rotating one vector to another. So it's sometimes useful to find a transformation that perform rotation align one unit vector to another. We can do it the hard way by using the previous routine. But then it's a lot of trig functions and also numerical unstable. And basically we will find out, we will do like the inverse trig function and then trig function. It's just not good way to do things. So a different way to do that is using this so-called Household matrix.
I don't think I've heard that term before.
Me neither, but it looks really nice. And it's just some dot product. I will skip the detailed maths, but I think, yeah, this is definitely worth understanding. Look at transformation is another useful operations. I guess I will skip this again.
The look at, I just want to editorialize and say, I think the lookat function is a disservice to learning linear algebra because it's magical. It takes three vectors that are really describing how you construct a matrix and then doing something weird and just assigning vectors to various to matrix columns or rows. And I found it much more intuitive to construct just okay, rotate the x-axis, rotate the y-axis, rotate the z-axis to point in the direction you actually want. Whereas I understand the point of a lookat is you have a point and you have a direction you want to look in. This is like a camera's definition, but for a ray tracer, I don't think it matters that much. For like a game where you're doing a lot of camera manipulation every frame, that's a bit different, like animation and stuff.
Yeah, a lot of times when I'm doing the path tracing stuff, I'll actually just be passing like x, y, and z basis vectors, which is basically a 3x3 matrix. But
Yeah.
I mean, that's what you get out of a lookat function is a 3x3, well, actually 4x4
Mhm.
vector or no, matrix. Sorry, but yeah, sorry, that's just my opinions.
Yeah, but you're right. Like, lookat is better, can be better understood as some kind of transformation, some kind of rotation of basis. It's just how it is rotated.
Yeah,
It's magical.
yeah.
a couple of cross products. Yeah.
I guess I'm just the construction of it is confusing more than the actual point of it. But anyways, yeah, let's move on.
So now we need to apply transformations to various objects, including points, vectors, like normal vectors, and even rays, something different things basically. And for point, basically we will perform the matrix multiplication of the matrix and this column vector x, y, z, and 1. I don't know why the code doesn't do matrix multiplication, but instead do it in the hard way. But just to save a little bit of computation, I guess. I'm not sure whether the optimizer can figure it out though. So let's also apply inverse method for each types, including point, to apply its inverse transformation to a given point. For vectors, it's very similar. So the multiplication is simplified because the homogeneous W coordinate is 0.
Just cancels out, so it's 0. So
Yeah,
don't need to do that
just don't do nothing. Sorry, I did not double negation in my talk. I don't know, like I think they should have provide some kind of slice notation for their matrix. I don't like they do this kind of hard way, but yeah, I guess it works. And for normal is a bit annoying because it's inverse. All the transforms are the inverse of an actual matrix. So yeah, when we do the inverse. Otherwise, it's identical to the vector version.
Yeah, there's some sort of transpose that happens there. As I remember, it's yeah, one of those early OpenGL class things. To learn why your normals aren't working correctly. You do perspective projection and stuff like that.
Yeah, transpose.
Isn't there?
Oh yeah. Oh
yeah, I
yeah.
think
I definitely implemented this myself before, but I forgot about this.
yeah, that's one of those details that's doesn't really follow any kind of logical pattern. You just kind of have to remember it. Yeah.
I had a fun time explaining to a friend the whole reason why the whole inverse transpose thing happens, and I drew a nice picture of a circle on a whiteboard, just like that diagram there. Now, when you stretch it or squash it, it doesn't look right.
Yeah. Well, I like the geometric algebra interpretations. Like a normal is not a normal vector. Yeah, for rays, we can transform its origin and direction. But PBRT has specific things to manage floating point roundoff errors. So they have small adjustment to transform ray origin. And it's defined in a later chapter. Bounding box, we just transform all the points and then recompute the min and max point. Composition of transformations is just basically matrix multiplication. And of course, we need to do the inverse in opposite direction when we do the multiplication. Yeah, because of this identity. So certain types of transformation can change the coordinate system from left hand to right hand. And so it's good if we can detect that.
Wait, what kind of operations do that? Like in that a surface normal always points outside. Oh, Oh, yeah. Okay.
I need to study
So
linear algebra a little bit more. Yeah, the determinant stuff is, I never learned enough of that.
yeah, I don't know how this happened. Determinant of transformation is negative means the handedness change. I think there are some deep wisdom here, but I don't have it.
Well, the logic that like strikes me as is basically you're inverting one of the axes, right? Because that's the handedness change, right? And then leaving the other ones untouched.
Oh.
Determinant is like assigned volume. So if the
Yeah,
sign
determinant is
Determinant.
a signed volume, basically. It's a signed volume of the parallelogram of three axes. Oh, and then if we flip one axis, the determinant become negative. Now it makes sense.
Yeah.
Yeah, I'm gonna have to look at the determinant piece of that a little bit more, but the flipping the one axis makes sense to me.
Vector frames. So this class just store a frame as three basis vectors, I assume. Yeah. So I think ray tracing in one weekend also has this class. It's called it's called OMB, like orthonormal basis, same kind of stuff.
I kind of prefer orthonormal basis, if only because frame is an overloaded term. You know,
Yeah.
frame of animation, window frame,
Frame of
frame
mind.
buffer. Yeah, thank you. Yeah.
Yeah, frame means so many different things, even just in this context.
Yeah, the math
Mhm.
alone. So this is a 3x3 class, a 3x3 matrix rather than a 4x4. So if you're only doing rotations, then this is what you'd use. Also scaling, but
Yeah, this is 3x3, and also it's a special 3x3. It's needs to be also normal. That's why we have a dedicated class for that. It has like this invariant in it. And now for people who don't know, orthonormal just means all three vectors are orthogonal to each other and all of them are unit vectors. And also, we don't need the inverse. We don't need the inverse because for orthonormal matrix, the inverse is just a transpose. So for example, rotation matrix is orthonormal, and rotation's inverse is just its transpose. It's the same kind of thing here.
Interesting.
I like they have this class rather than just using matrices everywhere, because as they said, with this class we can do some we can do some things without trig, which is really nice. The last section of this chapter talks about interactions. I think this is just basically ray something intersection point and all its data. So we have data like the intersection point. At time, I think the time can be used for stuff like motion blur. And also this out vector. For certain interaction points where the notion of outgoing direction does not apply, then the value is 0.
Interaction is a very interesting kind of a way to think about that. Yeah.
Yeah, I think the term that I've seen more often used are like intersection point or hit, something like that.
Mm-hmm. Yeah. Interface. I don't know, something like that.
Also, they use whether this normal is 0 or not to distinguish between whether it's a surface intersection or it's a media intersection. I'm not sure if I like that. I feel like if it's me, I would just not store normal in the median intersection at all. And they also have this kind of downcast. And the surface interaction, since surface interaction is a subclass of interaction, but I guess it's non-virtual. That's why they need this kind of stuff. Yeah, nothing is virtual. It needs to work on the GPU. It also stores partial derivative for what is P?
Point
Point?
rather than normal.
Yeah, it's a point.
Yeah, just like the
The
position,
later is normal. Yeah.
like the
Okay, yeah.
position. Yeah.
You see on figure 330, the point is the dot in the middle there.
Yeah. Yeah, I see.
Wait, are they storing the partial derivative of the surface at a point?
Yeah.
Hmm.
With respect to U and V.
Hmm.
Oh, I'm sorry.
I guess it does depend on the direction. I guess if you could store X and or U and V separately, then you don't have to. But no.
What those used for? Like texture mapping kind of stuff?
I think
Yeah,
so.
maybe MIP selection, something like that.
I mean, there are uses for partial derivatives in various shading things, but nothing super obvious. Like I'm saying, nothing super fundamental. There's like fun things you can do with them, but they're not really related to ray tracing or general shading problems.
It would probably come up
Yeah.
in texture mapping stuff, yeah.
Yeah.
Yeah, that's the main use I can think of.
So a second instance of the surface normal. Represent possibly perturbed values of these quantities. Does that mean this surface normal is the real normal, while the previous surface normal is always the normal of the flat geometry? Otherwise, why do we need to store two normals? Kind of confusing.
Shading normal, it might be like a normal map kind of thing, or
Yeah, this is the real normal, like after applied the normal mapping, and the previous normal is the normal of the geometry.
Well, here the dn du looks like it's the partial derivative of the
Yeah,
of it.
yeah, those are partials. I was more confused about this. Yeah,
Ah,
why they
yeah.
need to store the normal again?
I guess the original normal, the geometry normal is for like displacement mapping or something.
Yeah,
And this shading.
yeah, I guess so. PBRT has mechanism to flip normal. PBRT has each integer index for each face of a polygon mesh. Do they have a like per face texture kind of thing? That's why they have this? Probably. And whenever like the shading coordinate frame is computed, we just set all of its variables. And for the surface normal, we need to make sure it's points outward. So we need to do a branching here. Medium interaction represent an interaction at a point in a scattered medium like smoke or clouds. So it's a volumetric stuff. It don't add anything, any of those partial stuff to the interaction. So but instead it add a phase function member, which will also be described in
Much later chapter.
yeah, much later when we talk about like volumetric stuff.
Of course, when it says medium interaction, my first thought was small, medium, and large. Why do we need separate ones? Oh, medium, like a scattering media.
Yeah.
This is okay. Book recommendations, as well as
Yeah.
papers.
Book recommendations. Actually, I find
stuff.
some of the stuff in here interesting, like coordinate free. It's a word I never heard about, but sounds interesting. So probably read about it.
Coordinate-free video game development sounds like a marketing term to appeal to people who really like non-GMO, range-free, various other types of
All natural.
food production stuff.
Interesting.
Yeah. Also whatever this, yeah, encoding coordinate system using type system.
Yes.
This also sounds really interesting, but I don't know. It's also sounds really annoying, like Rust lifetime annotation. If you need to write that for every matrix.
I remember
So,
seeing
but-
there was a CPPCon talk that was about somebody writing some sort of type system for physics calculations. It was sort of remind me of that.
Yeah, interesting stuff. Definitely worth exploring. Especially, I also have an interesting in PL stuff, and this just sounds really interesting. Like more book recommendations. Oh, this immersive math. I actually find myself a bit hard to read this book for some reason. I prefer traditional linear algebra sources to this book for some reason, but other people may enjoy it.
I do like that it has the molar name in it, which is known for the molar very triangle plane intersection, or like ray triangle intersection algorithm.
Triangle. Is this
Yeah.
same person?
I would think so, but I could be wrong.
Molly
really
Petrumbor.
nice.
I think it is the same. Yeah.
Wow.
Let's see. Muller Trumbor is named for Thomas Muller.
T dot molar, even more.
And yeah, also paper recommendations for various like little techniques used in this chapter. And yeah, they have this paper we just read.
Yeah, that's funny. For fun, coincidence.
Not fun since we read this paper because we read the PBRT.
Just happenstance, really.
Yeah. Exercises sound nice. I will probably actually do it. Let's stop recording here.